Good afternoon. My name is Philip Gauthier, and I'm a graduate student at Penn State University, where I'm pursuing my Master of GIS degree. Today I'll be discussing my capstone project for this degree, in which I've combined my studies in geospatial systems with my work experience in precision viticulture to assess the spatial and temporal stability of seasonal vine biomass as characterized in Northern California vineyards. Put simply, California is a wine-producing powerhouse. Over 600,000 acres of vineyards produce around 80% of America's wine every year. In 2019 alone, California produced an estimated 4.2 million tons of wine grapes that were processed into just under 3 billion standard-sized bottles of wine. There's so much wine produced in California that if it were a sovereign nation, it would be the fourth largest producer in the world, behind only Italy, France, and Spain. The important takeaway here is that the state contains a lot of vineyards of all different calibers, and effective long-term management of them is vital for the state economy and the livelihood of local growers. One of the most fundamental parts of managing any vineyard is understanding the size and healthy fruit production capacity of the vines that comprise it. Quantifying the amount of vegetative tissue in a single vine or in a whole vineyard can allow growers to better understand their annual crop performance, and when combined with other vine performance metrics such as crop yield, it can help guide vineyard management decisions throughout the growing season. Growers may also use their vine size data to predict future vineyard performance using multiple growing seasons of vegetative data combined with vintage-specific climatic information. Regardless of what end goal this information is used for, any of these decisions can be made more robust or more reliable by starting with stronger, more accurate data on vine size. What is all this data used for, and how are vineyards managed in the real world? Typically, vineyard properties of any size are subdivided into blocks. Blocks can be delineated for many different reasons that might contribute to variations in vine performance, such as different soil compositions, microclimate, vine spacings, or simply different grape varieties. Often these blocks represent a management unit for growers, and uniform treatments are applied throughout, but many growers may also split their blocks into different subblocks. Some growers who are even more adoptive of precision viticulture methods may work towards variably applying management practices across space within a block. Regardless of how precisely the vines are managed, quantifying performance leads the way in decision-making throughout a vintage. So, what kinds of tools do growers have to measure the size of their vines? Some of the more common strategies used are shown here: pruning weight measurements and aerial NDVI imagery. Pruning weight is a tried and true method of quantifying vegetative production that has been used reliably for decades to understand vegetative capacity with simple measurements and well-established guidelines for most grape varieties. Measuring pruning weight accurately requires hands-on work, and though it is reliable for gathering point data, it is not well suited for gathering data of high spatial resolution or data over large geographic areas due to the manual labor required for a single vine measurement. An alternative method for assessing vine vigor quickly and accurately is using NDVI imagery. Unlike pruning weight measurements, NDVI can measure large geographic areas very quickly and with relatively little physical labor input. Despite these advantages, there is one major flaw. Vegetative indices such as NDVI are useful for defining variations of vine vigor and delineating relatively strong or weak zones, but thus far have not proven useful for measuring quantified vine size. Users are given a spectrum of values from high to low vigor, but not an absolute quantity of vegetative production. NDVI images can also be difficult to calibrate in vineyards for a number of reasons, including atmospheric interference, image timing, and the inherent three-dimensional structure of a vineyard canopy that is difficult to quantify from above. In recent years, a new technology has emerged that measures vegetative growth of a vine with absolute values both quickly and accurately. This device is known as the Physiocap system, and it functions by measuring individual cane diameters with a laser micrometer. This system was originally developed and designed by the Interprofessional Committee of Champagne Wine. Two sensors pass along opposing sides of a vineyard row and measure all the shoots that pass through the laser array, recording shoot diameters with a 1/10 millimeter accuracy and geolocating all measurements. Data is then taken from the field and processed either in a desktop or a web-based GIS platform for data filtration, biomass computations, and interpolation into continuous raster images. What starts as a database of point diameter measurements recorded by the device is eventually processed into a continuous image, much like an NDVI, except this image actually displays wood biomass values, rather than a spectrum from high to low. Biomass is represented by the wood index value, which is the sum cross-sectional square millimeters of all canes per square meter of vineyard ground area. Physiocap's rapid and accurate data collection platform positions it as an excellent tool for studying the spatial distribution of vine wood biomass over multiple vintages. The project that will be explored today used a large multi-year Physiocap database collected throughout Northern California's wine-growing regions to assess vineyard wood biomass distributions in 3 different aspects. Number 1, the spatial variation of vegetative biomass within a single block. Number 2, the annual variation of whole block mean values. And finally, the temporal stability of any spatial variations observed within a block. That is, to what degree do the locations of high and low vigor zones remain stable over multiple growing seasons? As a secondary focus, the project sought to analyze these results in the context of select block-specific attributes, including grape variety, rootstock, vineyard age, slope, and aspect. The ultimate goal of this second portion was to better understand if the variations highlighted during Part 1 of the project showed statistically significant levels of variation between groups when divided among those attributes listed above. For example, does the level of spatial variation of vine biomass differ significantly among blocks with different slopes? The Physiocap database that serves as the foundation of this project was compiled and owned by my employer, Fruition Sciences. The company has been providing Physiocap services to growers in the United States since early 2016, and on average, they collect around 180 hectares worth of Physiocap data every growing season. Data was compiled between 2016 and 2021, but due to the timing of the Physiocap scans after leaf fall, this data truly represents the vegetative growth of the 2015 to 2020 growing seasons. The image on the right shows what raw, unprocessed Physiocap point data might look like immediately after field collection. Each point represents 1 second of system runtime and may contain up to 50 individual shoot diameter measurements. For reference, the block shown here is approximately 4 hectares in size, and the data collection took just over an hour for the whole block. For this project, Physiocap data like this was combined with a vineyard blocks geodatabase. This vineyard geodatabase primarily consists of polygons representing block boundaries, but also contains block-specific information including grape variety, rootstock, planting year, vine spacing, and many more. All valid Physiocap data for each year between 2016 and 2021 was processed using a combination of QGIS and Microsoft Excel. Typically, data is processed through a QGIS plugin or through third-party websites, but the unique and large-scale nature of this project required a custom solution and control over process parameters. Data was first filtered to remove points of poor GPS quality and operation speed, 2 attributes of every point. Points with no vines measured were removed, as well as those outside block boundaries. For the remaining points, a filter was applied to remove any individual shoots less than 5 or greater than 15 millimeters in diameter. This would remove vine tendrils and trellis equipment from the measurements. Wood index was calculated at each measured point after filtration according to the equation shown here. This measures on a per point basis the summed cross-sectional area of all vine shoots per area of vineyard, measured in millimeters squared per square meters. Once the final calculations were completed, an inverse distance weighted interpolation was carried out using the same GDAL tool for QGIS that is specified in the Physiocap documentation. The end result is a continuous raster layer of wood index for each block. Once the final rasters had been generated, each raster image was loaded into QGIS. Each block was batch processed through QGIS's built-in zonal statistics tools to calculate the mean wood index value and the standard deviation of wood index values per block. Next, pairs of images were run through MATLAB's image analysis toolbox to calculate the structural similarity index value for each pair of years. This value ranges from 0 to 1 and represents the level of similarity between any 2 given images, with a value closer to 1 representing a more similar set of images. Many of the blocks scanned in the Physiocap database had only 1 year worth of data, and only those with multiple years were analyzed for their S value. These structural similarity tests were performed for those blocks with adjacent years of data, for example, 2017 and 2018, and also for those with either a 1 or a 2 year gap in between measurements. Once all block level calculations were completed for all data sets, these values were first examined using SPSS statistics to determine their normality when grouped according to the block parameters in the column on the right. Nearly all datasets showed non-normal distribution when subdivided into these different groupings. Due to this non-normality, the Kruskal-Wallis H-test was chosen as the non-parametric alternative to a one-way analysis of variance. This test is used to determine if there are statistically significant differences between values in two or more groups. 5 separate values characterizing the wood index were tested with 5 different grouping schemes, meaning a total of 25 different Kruskal-Wallis tests were performed using SPSS statistics. The results of the Physiocap calculations as a whole were tested using basic statistics to answer the questions posed in the project goals. On average, the measured blocks displayed 194.34 square millimeters of cane wood for every square meter of vineyard floor, with an interquartile range of 78. This block level mean value showed that it may vary by an average of 24.7% between any two growing seasons. Across space, within a single block in a single year, wood index values showed an average variation of 33% of the block's respective mean. Lastly, the mean S value for all measured blocks was 0.5, indicating only a moderate degree of temporal stability for spatial distributions. The 25 Kruskal-Wallis tests were performed with a significance level of 0.05. With these conditions, the results showed that 3 main descriptors of wood index behavior had significant differences between the groups. Blocks grouped by their rootstock or by planting year showed statistically significant differences in mean wood index, relative standard deviation, and SSIM values. Grape variety, aspect, and vineyard slope also showed significant differentiation with at least one descriptive measure of wood index. One measurement notably missing here is the maximum seasonal percent change, which showed no significant difference between any of the groups tested. Overall, the results of this Physiocap analysis reflect the results from similar previous studies. Average biomass, or in this case wood index, shows significant variation across multiple growing seasons, while simultaneously displaying significant variation over space within a block in a single year. Measures of spatiotemporal stability show only a moderate degree of stability over time, which departs slightly from previous findings in which pruning weight was used as the metric for defining biomass. This lower level of stability may be due to the uncontrolled nature of the data collection used for this project, and potentially could be higher with a more careful, precise data collection regimen. When the dataset was divided into groups by the 5 block parameters outlined previously, values of spatial variation, spatiotemporal stability, and block mean wood index all showed significant differentiation among several groups. Rootstock and vineyard age showed significant differentiation with all 3 of these measures. Despite these significant differences, each block is unique in its behavior, and the best way to understand its performance is to directly measure it using precision tools. Proper interpretation of these results requires some discussion of the limitations of the data used. First and foremost, this project was not a controlled experiment. These Physiocap data were collected by various vineyard employees and equipment operators over multiple years. Physiocap operation does require some basic training for any operator, but protocols or conventions likely vary by person or by year. Additionally, improper operation or poorly maintained equipment may have resulted in other errors in the data. Data auditing and filtering are performed as the first step in Physiocap analysis in an attempt to limit this degree of error, but these should be considered nonetheless. Those blocks with very low quality or very sparsely collected data were excluded from the final dataset. Many blocks did have only 1 year of usable data, meaning that the datasets used for multi-year measures of variation were less robust than the datasets used for calculating overall trends. There were a total of 344 individual blocks of data used in this project, 1/3 of which had 2 or more years of data. I'm going to finish today with a few key take-home messages from this project. Generally speaking, vineyard wood biomass as measured via wood index shows variation across multiple vintages and across space, even with consistent input through farming practices. These wood index characterizations show significant differentiation among blocks of different rootstock, age, or landscape, as well as some differentiation in mean wood index by grape variety. The final take-home message is that characterizing an individual block's vegetative behavior can be beneficial by allowing for more effective management. Growers may be able to monitor the effects of their vineyard practices, see the influences of seasonal climatic conditions, or use the data to develop corrective actions to achieve their production goals. I'd like to extend a sincere thank you to everybody who helped to make this project possible. At Penn State University, my advisor, Michaela Centenari, thank you for helping guide me through this process. I also want to thank Fruition Sciences for providing access to the data that served as the foundation for the project, and a special thank you to Thibaut Skolash at Fruition Sciences for providing guidance and expertise with the data. Finally, I want to thank all of you who tuned in to listen to the presentation. If you have any questions at all that aren't answered in the Q&A session, please feel free to reach out to me via email at my address listed here, or use the QR code on screen to find me on LinkedIn. I'll happily answer any questions you may have. Thank you.